Hello everyone, this is Purohit and you're watching my YouTube channel. In this particular video, I'm going to brief you with the basic concepts, only the essentialities of molecular orbital theory, and then we will proceed towards the application of that towards the homonuclear diatomic molecule. Alright, so first of all, let us begin with the very basics, not at the deeper level, but at the very basic level, what exactly molecular orbital theory is all about, so that when we discuss the application part, it gets into your brains very easily. So we begin with molecular orbital theory. It is in short also being abbreviated as MOT. Alright, so the basics are, the molecular orbital theory is based on covalent bonding. Now my dear friends, when we talk about covalent bonding, so the very first thing which comes in our mind is, yes, it's sharing of electrons. So covalent bonding is related to sharing of electrons. Okay, so the first point, I hope you're getting it, it's covalent bonding. What is it related to? Sharing of electrons. Now when you talk about electrons, so it's very obvious that the electrons are present inside the orbitals. So if the electrons has to be shared, it's common sense that the orbitals should mix with each other, it should combine with each other, it should overlap with each other. Then only sharing takes place. So sharing of electrons is related to overlapping, or as I use some other basic terms, this is a technical word, overlapping, or we can just say in simple English, it's mixing or combination of orbitals. Alright, so this is what we talk about. So once again, I'll just quickly go through it. Molecular orbital theory is based on a bond because it's related to molecule. So there has to be a bond. Which bond am I talking about? Covalent bonding. How it is formed? By sharing of electrons. What is the requirement? Overlapping of orbitals. Alright, got it clear up to this? Fine. Next, when you talk about a relationship between atoms and molecules, I guess every one of you know very well, its combination of atoms results in molecules. Yes, everybody knows this. So let us write it down, that combination of atoms results in what? Molecules. Okay, this is what is the basic line. So now, if we just bring about some changes into this particular statement, we get another statement. And what is that statement is that combination of, if combination of atoms gives you molecule, so it means combination of atomic orbitals will result in what? Oh yes, it's molecular orbitals. Alright, I've just used one extra word, and that is orbitals. Okay, so combination of atoms gives molecule, so therefore combination of atomic orbitals gives you what? Molecular orbitals. Or what is the technical word that we are going to use over here? Yes, it's overlapping. So overlapping of atomic orbitals results in molecular formation. Okay, and this is the way the molecular orbital formation takes place, because this is the basics, my dear friends. We have to understand that how the molecular orbital is formed. Okay, and then we can go ahead. Alright, so this was the introduction part. Okay, once again a quick recap, and that is that molecular orbital theory, the essentialities, the basics are being discussed in this particular video. So a molecular orbital theory is essentially based on a covalent bonding. Covalent bonding is going to be because of sharing of electrons. Sharing of electrons results in overlapping of orbitals. Right? And then combination of atoms gives you a molecule, so its combination of atomic orbitals gives molecular orbitals, or I just use a technical word, and that is overlapping of atomic orbitals results in molecular orbitals. I hope till now you're getting it right. Yes, my dear friends, now once we understand that how molecular orbital formation takes place, the basics of course, we now go into a general case. Okay, now I'm being very specific, I'm using the word general case. Okay, there are exceptional cases. I'm putting it in a block so you understand this, the importance of these words, that is general case. So what is that general case is? And that is, if I'm having n number of atomic orbitals. Now, just few minutes back I told you that molecular orbitals are formed by combination of atomic orbitals, or we say overlapping of atomic orbitals. Combination means it's very simple, there has to be at least two. If it's only one, how the combination takes place? Not possible. So at least it has to be what? Two. It can be more than that, alright. But the minimum criteria and for involvement of a combination, and that is two. So here I write it down. At least two atomic orbitals has to be there. Okay, at least two. I hope you understand this word very well. Alright, so the general case I'm discussing. So if I'm having n number of atomic orbitals, I will be having n number of molecular orbitals. That means, in other words, I will be having same number. Whatever be the number of atomic orbitals involved in the overlapping, same number of molecular orbitals are going to be formed. Alright, and that is, I still make it very simple. If there are two atomic orbitals involved in combination, how many molecular orbitals I'll be getting? Two. If the three are involved, so three molecular orbitals. If four are involved, four molecular orbitals, and so on and on. But my dear friends, as I said, the number is the same, but the energy is going to be different. Energy is what? Different. So when I use the word different energy, so it's very obvious that I will be having one set of lower energy, the other set of higher energy. Alright, so one half with lower, with the other half with higher. So as a result of which, what I'll do is, I make it as n by 2 and n by 2. Okay, I make it this way. Now n by 2 will be having what? Lower energy. The energy will be lower. Now you know very well, energy has a relationship with stability also. Alright? And that is inversely proportional. If a person is full of energy, then he's not going to sit at one particular place. He's going to roam around here and there, and that means he's unstable. So higher the energy level, lower is the stability level. So that means what? It's inversely proportional. So here when I say that one half I'm having lower energy, so that means we have a higher stability. Okay, the stable part is more. Alright, now next part is, you all know very well that the purpose of bonding is to achieve stability. So therefore, these are the set of orbitals which are contributing towards the process of formation of a bond. Okay, and therefore, I call these as bonding molecular orbitals. What am I going to call it as? Bonding molecular orbitals, or they are being called as BMO. Alright, this is about the first half. So now, you are very smart enough, I know that. So you understand now what is going to happen over here. Okay, the other half will be having a higher energy. If the energy level is higher, so obviously when you talk about its stability part, it's going to be less comparatively. Okay, it's a comparison part. So that means what happens is, this is going against the purpose of bonding, my dear friends. Okay, because bonding purpose is to go for stability, and this is going against the stability. Against means we call it as what? Anti, or we pronounce sometimes as anti. Okay, and therefore we call these as anti or anti-bonding molecular orbitals. Anti-bonding molecular orbitals, and therefore we are going to write it down as ABMO. Alright, so these are the general case. Once again, be very, very clear. Okay, I'm just discussing general case. So just have a quick wrap up with this, and that is, if we have n number of atomic orbitals, obvious, the condition applied, and yes, you know that it has to be what? At least two, because we talk about combination. Alright, so if there are n number of atomic orbitals, we have n number of molecular orbitals formed, same number, but energy is different. One half with a lower energy, the other half with a higher energy. The one with a lower energy are called as bonding molecular orbitals, the one with a higher energy are called as anti-bonding molecular orbitals. Alright, I guess up to this part is very clear. Alright, now one more point which I would like here to mention, and that is that I made a condition, that is n, the value of n should be at least 2. Okay, so it can be 2, 3, 4, 5, 6, 7 like that. So suppose if I say it's 7, okay, 7 is my lucky number, so I just consider it 7. So if I consider that n value as 7, so 7 atomic numbers, 7 molecular orbitals, so 7 by 2, it gives me 3.5. So am I going to say that 3.5 is bonding and the 3.5 is anti-bonding? No. Then once again, what we do for this is, okay, because this n value can be either odd or it can be even. So whatever discussion this has been done, okay, so this is when we consider n is going to be what? Even. Okay, and from there, this particular calculations and this particular considerations is done. But then what happens when n is going to be odd? Then once again, as a general case, please, I'm specifying these, my dear friends, as a general case, okay, it's not going to be applicable everywhere, okay, so as a general case, when n is going to be an odd number, then what is going to happen is, it's a very simple mathematics, and that is, if you are going to subtract 1 from any odd number, you always get an even number. Okay, you know this very well. If you subtract 1 from any odd number, you get an even number. So I'm going to subtract that. So it gives me n minus 1, and because it is even, I can exactly divide it by 2. So it is n minus 1 by 2. Okay, similarly, I will be having n minus of 1 by 2. Alright, so this, you know very well what am I talking about? Oh yes, it's BMO, and this I'm talking about is ABMO. Now your question will be, where is that 1 gone? Okay, you have subtracted 1, so where is that 1? So that 1 is not involved in bonding. Okay, that 1 is not involved in bonding, and I call it as non-bonding. Okay, what am I calling it? Non-bonding. But then once again, inverted commas please, I stress on this word, this is just a general case. Alright, so these are the two cases where we have n as even, so this is what happens. If we have n as odd, then this is what happens. But then, as I told you, that these are not the specific molecules that I'm talking about, I'm just talking about the general case. So, I guess you have understood up to this very well. Now my dear friends, once you have understood the concept of what is bonding and what is anti-bonding, let us now discuss about those two molecular orbitals in much more detail. And that is, they are basically orbitals, and the orbitals are made up of what? Electrons, because electrons goes into those orbitals. Now when we talk about electrons, electrons have got two types of properties. One is a particle property and the other is a wave property. Definitely you have heard about a concept called as wave-particle duality. Okay, dual means two. Okay, so here electrons, as I said, particle as well as wave property, but here in this particular context which I am referring to, we are going to consider the wave properties. Okay, we are going to consider what? Wave properties. And everybody has known that how does the wave travel? Okay, it goes up and down, up and down. So the same thing has to be considered over here when we consider bonding as well as anti-bonding. So I'll just show you by means of a diagram. Let us consider a hypothetical straight line. Hypothetical means it's imaginary. And now I will be showing waves. Now with respect to this hypothetical line, I am now in a position to define the upward wave and the downward wave. Okay, I give numbers also so that you understand this very well. 1, 2, 3, 4. Alright? I denote an upward wave as plus sign and the downward as minus. So plus, minus, plus, minus. Now what are these plus and minuses? See, I am using the word signs. Okay? And signs are known as, what are they representing? Yes, directions. Okay, they represent what? Directions. Okay, please be very clear. They are not charges. Okay, because please my dear friends, as we go ahead you will understand that why am I not talking about charges? Because the entire concept becomes opposite. So please, I am stressing on this word, okay, and you try to understand that plus and minus, they stand for what? Signs, not charges my dear friends. And what does the sign indicate? Directions. Alright, so it means if the signs are same, the directions are same. If the signs are opposite, the directions are opposite. Okay, so let us consider now 1 and 2. Now if these two waves, if you can consider, one is plus, the other is minus. So they are opposites. Okay, if I consider 1 and 3, if I consider 2 and 4, they are having what? Same signs. Now, as I told you about bonding and anti-bonding, bonding is contributing towards stability. And what is the another word for stability is strength. Okay, it gives you what? Strength. So it's very obvious that when two people have to go to a same destination, so obviously they will go together, and when they will go together, it will be obviously resulting in what? Strength. But if one has to go on to the east and the other has to go towards the west, so obviously they cannot go together, so they have to go alone. So that is resulting in what? Weakness. So strength, okay, is nothing but bonding, and weakness means it is anti-bonding. Okay, so that is the way you need to remember. So when you talk about signs, if the signs are same, the directions are same, so they will go together. Okay, if the signs are opposite, the directions are opposite, they cannot go together. So when they go together, it's strength, it's bonding molecular orbital. When they cannot go together, so that means it's weakness, and it is anti-bonding molecular orbital. Alright, so this is what is the relevance with respect to what? Sign. So if I'm going to talk about waves, which is like 1 and 3, I will call it as BMO. Similarly, 2 and 4 also can be called as BMO. Okay, we are not considering whether it's minus and plus, we are just considering whether the signs are same or opposite with respect to each other. Okay, then whether both of them are plus or whether both of them are minus. Okay, but then we are just going to consider whether it's same or whether it is opposite. Okay, so 1, 3, 2, 4, they are BMO. But if I'm going to consider 1 and 2, or if I'm going to consider 2 and 3, or if I'm going to consider 1 and 4, then the signs are opposites. And that means it will result in what? An anti-bonding molecular orbital. Alright, so this is with respect to what? Wave functions, or with respect to the wave properties. Why we are going to consider that? Because we are considering the electrons to have the wave properties. Of course, it is having a particle property also, that is scattering of light is one of the basic particle property, but then we are going to ignore it as far as this particular concept is going on. So with respect to the wave properties, this is what we can define the bonding as well as the anti-bonding on the basis of, my dear friends, I stress on this word, okay, and that is what? Signs. Alright, now next part is, now if I have two atoms, okay, let us consider that two atoms as A and B. Okay, if I got two atoms, now these two atoms will have orbitals, obviously. So these orbitals will combine, will overlap, resulting in the formation of what? Molecular orbitals. As I told you, if there are two orbitals involved in combination, I will be getting two molecular orbitals. One half will be bonding and the other half will be anti-bonding. Now since here I am going to consider the wave properties, so I will be considering or introducing a parameter called as wave function. What I will be considering? Wave function. And that wave function is denoted as what? Psi. Okay, so let us still consider this. Wave function. Function means dependence. So it is dependent on the wave property. It is denoted as what? Like this. And what is it called as? How do you pronounce it as? Psi nahi bolna hai. You have to pronounce it as what? Psi. That is P is what? Silent. Alright? So let us have simple hydrogen molecule. Okay, a hydrogen molecule is H2 molecule. There are two hydrogen atoms. So let us consider those two hydrogen atoms as A and B. Alright, so when these wave functions of these orbitals combine, they will give you a bonding molecular orbital as well as anti-bonding molecular orbital. So, according to LCAO, how the wave functions can be represented? What is LCAO? Linear combination of atomic orbitals. What is it? Linear 1:1 combination of atomic orbitals. So on the basis of this LCO, how we are going to write it down is psi b is equal to psi a plus psi b. Psi a is equal to psi a minus of psi b. Now what is all this? I'll tell you. Psi a and psi b are the wave functions. of the atomic orbitals of A as well as B. Okay, psi small b is the wave function, I just write it down in short, WF of what? BMO, and psi A is the wave function of what? ABMO. I hope you understand this full term. The full forms of this, yes, BMO is bonding molecular orbital and ABMO is anti-bonding molecular orbital. Alright, so you can see now, check it out from this particular part. And that is bonding molecular orbital is formed by addition of wave functions, and anti-bonding is formed by subtraction of wave functions. Addition results in strength, and I told you bonding molecular orbital is related to what? Strength. Subtraction results in weakness. Okay, and that is anti-bonding. Anti-bonding relates to weakness, the bonding molecular orbital relates to strength, and that's the reason we are going to go for this signs, the additive signs and the subtractive signs. Alright, now when you go for the normalization of these wave functions, okay, we get some complex terms out of it. Okay, but if we are going to, because we are going for more simpler terms, that is what my purpose is, कि जितना हो सकेगा उतना simple terms मैं आपको explain करूँ ताकि आपको जल्दी आसानी से समझ में आ जाए. तो normalizations की जब हम बात करेंगे of these wave functions, और उसमें यदि हम overlap integral को ignore करते हैं. Now what is overlap integral? Don't worry, I'll explain it. Okay, it is denoted as capital S. Okay, लेकिन अगर यदि हम उसको ignore करते हैं तो the wave functions that I get by ignoring the overlap integral, and that will be psi b will be equal to 1 upon root 2 psi a plus psi b, and psi a is equal to 1 upon root 2 psi a minus of psi b. Okay, so this is what we are going to consider, the wave functions of the bonding as well as the anti-bonding molecular orbitals by ignoring what? The overlap integral. Okay, what is that overlap integral? I'll explain you, okay, in the later part. Okay, but I guess up to this part is being very clear to all of you all. When I was referring towards the wave functions of the molecular orbital bonding as well as anti-bonding, I made a mention about a term that was overlap integral. Okay, and I say that overlap integral, what exactly it is, I'm going to explain you in the later part. So right now, I will explain you that what exactly is overlap integral. Now my dear friends, in simple words, overlap integral, symbol is what? S, is the measure of the extent of overlapping of the atomic orbitals which results in the formation of molecular orbitals. Okay, that is what overlap integral is all about. It is the measure of the extent of overlapping. Now see my dear friends, it's very simple. Whenever we talk about a bond which is being formed, it's forming by overlapping of atomic orbitals. So now the strength of the bond depends upon to what extent the overlapping takes place. Okay, if I'm going to show a very simple demonstration over here, and that is if I consider my two hands as the atomic orbitals, then please have a look at the fingers now. If I'm going to show it like this, there is an overlapping, yes. Okay, if I'm going to show it like this, there is an overlapping also, but then the extent of overlapping differs. So here the extent of overlapping is less, okay, and therefore the bond strength is less. Here the extent of overlapping is high, is more, and therefore the bond strength is also more. So that means the extent of overlapping is directly related to what? Strength. And that is being indicated by means of overlap integral, and that is being termed as alphabetically is capital S. So therefore we just simply say S is directly proportional to the strength of the bond. I hope it is very clear. Okay, so S is overlapping integral, it is the extent of overlapping. So greater the S value, greater the overlapping, and greater is the strength. So S is directly proportional to the strength of the bond. So now, when we are going into the values of S, let me be very clear. The values that which I talk about are three values. a positive value, a negative value, and 0. Alright, so you know very well, when I've already explained you about bonding and anti-bonding, and I'm very sure everybody has understood also. I'll give you a full guarantee about it because I know my students very well. They are very smart enough. So अभी तक जो भी मैंने आपको कंसेप्ट समझाया वो आपको बिल्कुल समझ में आ गया होगा और उसी के आधार पर आप ये भी जानते हो कि जब हम बॉन्डिंग और एंटी बॉन्डिंग की स्ट्रेंथ की कंपैरिजन करेंगे तो बॉन्डिंग का स्ट्रेंथ ज़्यादा होता है एज कंपेयर टू एंटी बॉन्डिंग, यानी बॉन्डिंग का एस वैल्यू ज़्यादा मतलब मोर मतलब पॉजिटिव। ओके, सो एस वैल्यू हैज टू बी पॉजिटिव फॉर बॉन्डिंग, एंटी बॉन्डिंग का वैल्यू कम होता है मतलब नेगेटिव, और नेगेटिव मतलब लेस देन 0, यानी एस का वैल्यू शुड बी लेस देन 0। Are you recording it? Okay, so you go into S value is greater than 0. Okay, तो वो हो जाएगा क्या? BMO. S value less than 0, it is going to be what? Antibonding molecular orbital. Now what about S is equal to 0? Okay, याद है मैंने बताया था आपको non-bonding. I consider that as a general case. Okay, the general case where we are going to subtract 1. Alright, so that is going to be what? Non-bonding. So here in this case, what we say is the atomic orbitals are not interacting at all. Okay, so as a result of this, there is no change in the energy. Okay, whenever there is an interaction, there is going to be a change in energy. Please, my dear friends, keep this in mind. Okay, so here it is because there is a positive interaction, so energy gets lower. Here there is a negative interaction, so that means the energy rises. But here there is no change in energy because there is no interaction at all between the atomic orbitals. Okay, and therefore I say that there is no change in energy when we compare it with respect to the corresponding atomic orbitals. Here the bonding molecular orbitals have got energy less. Here we say energy high as compared to what? The atomic orbitals which are involved in overlapping. Okay, because this is comparison. Whenever I say high energy, low energy, so it's always comparison. Okay, so with respect to the atomic orbitals, when the energy of the molecular orbital gets lowered, then that molecular orbital is called as bonding. When the energy of the molecular orbital is raised, I call it as anti-bonding. And when there is no change in the energy at all, so that means we call it as what? Non-bonding. So that means there is no interaction at all in the atomic orbitals. Okay, and hence there is no change in energy. Okay, so this is, my dear friends, about overlap integral. And I'm very sure you got this right. Yes, my dear friends, now once we have understood what is overlap integral and how it can be related with respect to the bonding, anti-bonding, and you have also understood what is anti-bonding molecular orbitals, what is bonding molecular orbitals, okay? So now a quick recap of what exactly are these two orbitals by means of what differences, a distinguishing part or a comparison between bonding as well as anti-bonding. So here we go. I give a heading over here is BMO and here the heading is ABMO. So I just mentioned the important points over here. The first point is BMO is formed by what? Oh yes, it's addition of wave functions. By addition of wave functions. So I just write it down as WF. So here it's going to be subtraction of wave functions. So I've already explained you all these concepts. Only thing is I'm just going to jot down some points over here so you understand what is exactly the differences between the bonding as well as anti-bonding. Next one is, when you talk about the bonding molecular orbital, then we say that the waves have the same sign. Do you remember this? I told you. Okay, the plus plus and the minus minus. Okay, they have the same sign. Okay, signs means, yes, direction. They are not charges. So if the signs are same, the direction is same, so they will go together straight. As simple as that, my dear friends. Now, here what will happen is, the waves will be having, or they will be on opposite side. Okay, so that means they have got opposite signs. One is plus, the other is minus. Here, both of them are going to be plus, or both of them are going to be what? Minus. So same sign means same directions. Opposite sign means opposite directions. Right? Next, when you talk about the electron density, okay, when you talk about what? Electron density between the nuclei, obviously of the atoms which are involved in the overlapping, so that is going to be what? High. So between the two nuclei there are electrons. The two nuclei are having the same sign charges, positive, positive, but because there are electrons in between which is negative, so as a result of which positive and negative there is going to be a force of attraction. Alright, so here I am talking about charges, my dear friends. Here I told you about signs because it's very clear. I told you before also that the concept becomes opposite. अगर मैंने साइन की जगह पर चार्जेस ये शब्द यूज़ किया होता तो अगर एक वेव है पॉजिटिव वाला और दूसरा है नेगेटिव वाला, आप क्या बोलोगे? पॉजिटिव नेगेटिव, तो अट्रैक्शन होगा तो दोनों कंबाइन होगा, साथ में जाएगा. लेकिन दोस्तों ऐसा नहीं है, कंसेप्ट पूरा ऑपोजिट है. अगर पॉजिटिव और नेगेटिव है तो वो कंबाइन नहीं होगा क्योंकि पॉजिटिव और नेगेटिव चार्जेस नहीं है दोस्तों, वो साइंस है. इसलिए मैं आपको इतना स्ट्रेस कर रहा था ऑन दीज वर्ड प्लस एंड माइनस एज साइंस. ओके, लेकिन यहाँ पर जो मैं आपको बता रहा हूँ, एंड दैट इज टू न्यूक्लियाई, both the nuclei are positively charged. Between the two nuclei there is electrons which is negatively charged. So positive, negative, negative, positive. So there is force of attraction. So in other words we say the repulsions are going to be what? Less. Okay, here we will say the electron density between the nuclei is going to be, actually we have to say nil, but I am just using the symbol word that is less. Okay, therefore the repulsions are going to be what? High. Okay, now repulsions are related to energy, you know that very well. So the next point is the energy is less of the bonding molecular orbitals. Here we say the energy of the bonding molecular orbitals is high. Alright, the next one is it's about overlap integral. Just few minutes back I told you S value greater than 0. Here we say the S value is less than 0. Alright, so greater than 0 it's all about positivity, less than 0 it's all about negativity. So it's positive over here, greater strength, negative over here, lesser strength, and that is what we talk about between the bonding as well as antibonding. So my dear friends, this is a quick review of the comparison between bonding as well as antibonding, and I am very sure you have understood all these points very well. Now the next point which we move on, and that is about symmetry of molecular orbitals. Now under this category of symmetry of molecular orbitals, we are going to discuss about gerade and ungerade orbitals. Now I'll explain you by the means of a very simple example. We start with the s orbital. S orbital, we say it is spherically symmetrical. So if I'm going to show a plus sign over here, okay, many times it is being shown this way, plus sign at the center. So many of them feel that okay, only at the center it is positive. No, it's not like that. It's spherically symmetrical. Symmetry means what? Same. So the plus sign is going to be everywhere, it's going to be same. Alright? So what I do is, if I draw a line, okay, a diagonal, okay, I mark this as point A and I mark this as a point B. So if I'm going to draw a diagonal and if I'm going to go from point A to point B, I need to find out the sign. So at point A, the sign is positive, at point B, the sign is positive. So as I'm going to travel, so the two opposite points along the diagonal, the sign remains the same. Okay, and that is what we call it as even, or we call it as symmetric. Okay, and that is what we call it as gerade. Okay, gerade means what? It is even. But if I'm going to consider a p orbital like this, okay, these are the three axes that we talk about with respect to p orbital, the dumbbell shape. Okay, now if I'm going to draw a line like this is point A and this is point B. Now here what happens is both the lobes are different. Here we have only one lobe. They are different lobes. Now do you remember the condition for that? Okay, what about combination? Yes, I am sure you know it. What is the condition for combination is same sign. If the same signs are there, they will go together. But if the signs are opposite, they cannot combine. The same thing is over here. The fact that there are two lobes, यहाँ पर आप देख सकते हो कि ये दो लोब है. अब ये दो लोब क्यों हैं? क्योंकि वो एक नहीं है. और वो एक क्यों नहीं है? क्योंकि वो combine नहीं हो पा रहे हैं एक दूसरे के साथ. और वो क्यों नहीं कंबाइन हो रहे? क्योंकि साइन उनका ऑपोजिट है, यानी अगर एक प्लस साइन है तो अदर विल बी व्हाट? माइनस। यानी जब मैं ए से बी की तरफ जाऊंगा तो साइन चेंजेस, ए में नेगेटिव साइन और बी में पॉजिटिव साइन, जो यहाँ पर नहीं हो रहा। एज आई गो फ्रॉम ए टू बी द साइन डज नॉट चेंज, बट हियर इन केस ऑफ p orbitals, okay, this is an s orbital, this is a p orbital. So in the case of a p orbital, as I go from point A to point B, the sign changes, okay, and that means it is uneven, okay, or we call it as unsymmetric, or we call it as what? Ungerade. Okay, so gerade is being denoted as G and ungerade is denoted as U, okay, in small alphabets. So this is about, my dear friends, okay, with respect to the signs, with respect to similarity. Symmetry is all about similarity. We talk about two types of orbitals. One is gerade and the other one is what? Ungerade. If the signs remains the same, then we call it as, yes, gerade. But if the sign changes, then we call it as ungerade. Alright, so I'm very sure this concept is also very well understood by you all. Now, my dear friends, you have understood by now, and that is overlapping of atomic orbitals results in what? Molecular orbitals. Now we also talk about the strength of these molecular orbitals. So for the strength of the atomic orbitals, we also need to consider that these atomic orbitals, how they are going to combine. Okay, so that is with respect to axis. Okay, so there is an internuclear axis. We call it also as a bonding axis. Bonding axis by default we consider it as a z-axis. So with respect to the axis, how the overlapping takes place, accordingly we decide the strength of the molecular orbitals. Okay, so on that basis there are two types of molecular orbitals which you have already heard about, and one is sigma and the other one is, yes, pi. So let us briefly discuss about these two types of molecular orbitals. We have sigma molecular orbital and we have pi molecular orbital. So just important points I'm going to mention over here. The first point is, in this case, the overlapping atomic orbitals are along the internuclear axis. Along the internuclear axis. I'm just writing it short. Internuclear axis. Along the internuclear axis. Okay, here obviously you understand this. Overlapping atomic orbitals will be perpendicular to the internuclear axis. Okay, that is what you need to remember. Second point में क्या बोलेंगे? The electron density along the internuclear axis is going to be what? High. Okay, whereas here we need to say electron density along the internuclear axis is going to be nil. Okay, it's actually less, or we generally call it as what? Nil. Okay, that is pi molecular orbitals. There is going to be a free rotation over here. Okay, free rotation takes place when you are going to consider sigma molecular orbital, but those free rotation is not going to be possible over here. Okay, there is some sort of a rigidity as far as the rotation part is concerned in pi molecular orbitals. When you talk about sigma molecular orbitals, they affect the geometry of the molecule. It can be bond angle, it can be bond length, okay? Whereas here, it does not affect to a greater extent. Does not affect the geometry to a greater extent. It means to a certain extent it can, but not to a greater extent. Alright, when it is comparative, my dear friends. Okay, comparison कर रहे हैं दोस्तों पाई को सिग्मा के साथ. तो जितना सिग्मा असर करता है ज्योमेट्री ऑफ द मॉलिक्यूल पे, उतने हद तक पाई असर नहीं करता. Okay, that is what is being said. So this is, my dear friends, in just brief about the comparison between the sigma molecular orbitals as well as the pi molecular orbitals. Okay, sigma can be in bonding as well as anti-bonding. Pi also can be in bonding as well as anti-bonding. Okay, सिर्फ इतना याद रखिएगा कि when we talk about anti-bonding, we are going to use the mark star. Star mark क्योंकि stars are up there in the sky, ऊपर है, और anti-bonding molecular orbital का एनर्जी भी ऊपर है, इसलिए ऐसा स्टार मार्क करते हैं. तो ये आपको याद रखना है. तो यहाँ पर मैं लिख के रखता हूँ आपको कि अगर हम BMO की बात करें तो वी आर जस्ट यूजिंग द वर्ड सिग्मा, लेकिन अगर हम ABMO की बात करें तो वी आर गोइंग टू यूज सिग्मा स्टार. ओके, अब इसमें भी याद रखिएगा दोस्तों, whenever there are S molecular orbitals, okay, whenever it is S, it's always going to be sigma. It cannot be pi at all. वो याद रखिएगा आप लोग. ओके, सो यहाँ पर सिग्मा S, सिग्मा स्टार S ऐसे होगा. जब हम पाई की बात करेंगे, सो BMO we are going to consider as pi and ABMO we are going to consider as pi star. अब इसमें कौन से हो सकते हैं? 2px and 2py can be considered. Condition applied, we are considering Z as a internuclear axis. तो 2pz क्या होगा? सिग्मा होगा. ओके, तो जब सिग्मा स्टार की बात होती है तो इट कैन बी से 2s and it can be 2pz. It can be 1s also, please don't be that way. Okay, I'm just using the numbers that is 2, that's it. Okay, so 2h, 2pz can come under bonding and anti-bonding sigma and sigma star, whereas 2px and 2py when we are talking about, so it will be pi bonding and pi star anti-bonding. Alright, so this is about, my dear friends, a brief comparison between sigma and pi molecular orbitals.